Welcome to the deep dive, where we cut through the noise and get you straight to the core of what you need to know. Today, we're plunging into one of the most fundamental architectural dilemmas in the world of embedded systems. That's the choice between building your software directly on what's called bare metal or harnessing the power of a real-time operating system, an RTOS. This
Right.
isn't just, a technical implementation detail. It's a foundational decision that really shapes the entire project.
That's absolutely right. And this choice, it has profound consequences. I mean, for everything from how fast you can develop your product to the ultimate complexity of your system,
Right.
its long-term maintainability, how well it can scale to future needs, and perhaps most importantly, the total cost of ownership over its entire life cycle. It truly sets the trajectory for success or, well, struggle.
And what might surprise some listeners is how much the lines have actually blurred in modern embedded development. The old image of bare metal as meticulously flipping bits in hardware registers, well, that's largely evolved. Today, when we talk bare metal, we're often still interacting with sophisticated vendor-supplied software development kits, or SDKs.
Yep, the detail.
And hardware abstraction layers, exactly, known as HALs. So the choice frequently isn't between pure bare silicon and an RTOS. It's often between a bare metal plus vendor HAL stack and an RTOS plus vendor HAL stack. It really reframes the entire debate, doesn't it?
It absolutely does.
Over the next little while, we're going to unpack each of these paradigms, try to understand their core strength and their inherent weaknesses. We'll then put them head-to-head on key aspects like performance, resource use, and debugging. We'll also touch on advanced considerations such as multi-core processors and crucial safety certification requirements.
Important stuff.
And finally, give you a structured framework to guide your decision-making process for your next project. Okay, let's unpack this then. What exactly are we talking about when we say bare metal or RTOS in the context of embedded systems?
Okay, so at its simplest, bare metal programming means your application code runs directly on the microcontroller hardware. There's no operating system in between.
Right, on the metal.
Exactly. The developer is responsible for, well, everything. Initializing clocks, managing memory, controlling peripherals, sequencing all the tasks. Your program typically starts up, does some setup, and then enters an infinite while one loop, often called a super loop, which is the main program flow.
The main loop, got it.
An RTOS, on the other hand, is a specialized operating system. It's built specifically for real-time applications. Its core purpose is to manage system resources, things like CPU time, memory, peripherals, and process data and events within predictable, strictly defined time constraints. Deadlines.
Deadlines are key.
Crucial. It introduces an abstraction layer with services for multitasking, intertask communication, and synchronization. Basically, it helps manage the increasing complexity we see in today's embedded systems.
We just mentioned this blurring line, though, in modern development, where bare metal isn't quite so bare because of these HALs. So if bare metal development already involves a layer of abstraction from the hardware, what does that mean for the actual choice developers are making? Is it still a clear distinction?
That's a great point, and yeah, the distinction gets fuzzier. The choice frequently boils down to bare metal plus vendor HAL versus RTOS plus vendor HAL. And RTOS often builds on top of those same HALs, creating a consistent foundation. But what's important to note is that relying solely on a vendor's HAL still creates a form of hardware lock-in, right? Because your code is tied to that specific abstraction.
Right, you're locked into that vendor's way of doing things.
Exactly. But here's the interesting thing. A cross-platform RTS can actually mitigate this by providing a consistent application interface across different hardware and vendor ecosystems. So it's a bit counterintuitive, but the RTOS can sometimes increase portability compared to just using a vendor HAL.
Huh. Okay, so at their core, the philosophical difference is really about, say, direct hardware control versus managed complexity. And architecturally, it's sort of a single infinite loop versus a collection of independent tasks all working together, managed by the OS.
Precisely.
We've touched on the allure of bare metal's ultimate control. Let's really dig into what that looks like in practice and what architects hope to achieve with it. The philosophy here, as I understand it, is to gain direct, unfiltered authority over the hardware for meticulous optimization. Performance, memory, power consumption.
That's the goal.
For simple resource-constrained systems, it's often seen as the default because it gives you that absolute control.
Right. And even within bare metal, developers have come up with common architectural patterns to, well, try and bring some order. The most fundamental is the super loop, often called a foreground-background system. It's just that single while loop that sequentially executes functions,
Yeah.
read inputs, process, update outputs, repeat.
Simple enough.
Simple, but its primary weakness is unresponsiveness. If any single function in that loop takes too long, it holds up everything else. The system can seem slow or even miss events entirely.
Okay, so how do you get around that?
Well, the next step is often to introduce interrupt-driven systems. Interrupt service routines, or ISRs, allow the system to react to asynchronous events like a button press or data arriving by temporarily preempting the main loop.
So you get some basic multitasking?
Sort of, yeah. But it brings its own complexities. ISRs must be extremely short and fast. You can't do complex processing in them. And you need really careful management of critical sections, times when you temporarily disable interrupts to prevent race conditions when you're sharing data between an ISR and the main loop.
Right, if the ISR modifies data the main loop is using.
Exactly. One wrong move, your data gets corrupted, and these bugs are notoriously hard to find because they depend on precise timing.
Okay, what else?
As systems grow, developers sometimes evolve the super loop into a rudimentary cooperative scheduler, often using state machines. Here, you manually break the application into smaller chunks or tasks that are designed to run quickly and then voluntarily yield control back to the main loop or scheduler.
So they cooperate. They don't preempt each other.
Correct. This prevents one task from monopolizing the CPU, but this manual scheduling logic. It can quickly become convoluted and really tough to maintain. It's like trying to juggle, a dozen different things by yourself, meticulously switching between them. One slight misstep, one task takes just a bit too long.
And something else gets starved.
Precisely. Another critical function might never get its turn, leading to subtle, maddening task starvation. Imagine your sensor data not being processed because your display update loop got stuck somehow. That's the kind of silent killer you see in these systems.
So after all that, what are the big strengths of this bare metal approach? Why do people still choose it?
Well, there are definitely reasons. Firstly, maximum performance and minimal latency. With RTOS overhead, you can potentially get the fastest possible response to an interrupt. Extremely low and predictable latency.
For simple systems.
Yes, crucially, for simple systems. For simple, hard, real-time control loops, it can be excellent because you're directly manipulating the hardware. No layers in between.
Okay, what else?
Secondly, minimal resource footprint. Your code size, your ROM or flash usage, and your data memory, the RAM, are absolutely as small as possible. You only include what's explicitly required.
Which matters a lot on tiny chips.
A huge advantage for very constrained MCUs, maybe less than 32 KB of flash or 4 KB of RAM, where literally every byte counts.
And third?
And thirdly, complete predictability in simple systems. The execution path is linear, generally easier to follow. This makes timing analysis and verification easier, provided the system doesn't grow too complex. You can, in theory, trace every line of code.
You make a compelling case for the complexities that bare metal introduces as systems scale, though. But couldn't someone argue that really disciplined coding practices and, rigorous testing can mitigate many of these issues, maybe even make it more reliable than an RTOS with its own potential bugs?
It's a valid point, and disciplined coding is absolutely crucial, whatever approach you take. But the reality is, as the number of interactions and asynchronous events grows, the human brain just struggles to keep track of all the potential race conditions, the timing interdependencies, all the edge cases in a purely manual bare metal system.
It gets overwhelming.
It really does.
Yeah.
And what often happens is you end up inadvertently reinventing a primitive ad hoc operating system yourself. You build your own queues, your own basic scheduler, and typically it's less robust, less tested, and harder to debug than a battle-tested RTOS kernel.
Yeah, that sounds exactly like what people in software development call the technical debt cliff. You start with bare metal, think, oh, this is simple, this is fast. But then the requirements pile on, maybe add a command line interface. Oh, now we need a Bluetooth stack, integrate this new sensor. Suddenly you're forced to reinvent the wheel, right?
Yeah.
Creating your own primitive, often fragile versions of OS features like message queues or maybe some kind of task switching. You end up with what's basically a poorly conceived and hacked together RTOS.
Oh, yeah.
And that initial speed advantage is completely wiped out by crushing debugging and maintenance burdens later on. It's like you sprinted for the first 100 meters and then just fell right off that cliff.
That's a very good analogy. The initial simplicity is deceptive.
So if bare metal often leads us down that path towards the technical debt cliff, What's the alternative? What's the architectural parachute, so to speak? This is precisely where the RTOS steps in, right? Built fundamentally to tackle those very complexity problems. It seems to be built on three core principles. First, determinism, which isn't just about raw speed, it's about predictability. Guaranteeing a task will complete within a defined time every single time.
Exactly. Predictability is often more important than raw speed in real-time systems.
Second, concurrency, which is about structuring applications as multiple independent threads or tasks that appear to run simultaneously, letting you break down complex problems into more manageable pieces.
Right, divide and conquer.
And third, abstraction, providing a standardized API and application programming interface so you can focus on your application logic, not fiddling with low-level hardware bits and registers all the time.
Precisely.
Yeah.
It manages the underlying complexity for you. And we classify these real-time systems based on how strict those deadlines are. Hard real-time means missing a deadline is catastrophic. Think automotive, anti-lock braking systems, flight controls.
Lives are on the line.
Absolutely. Failure is not an option. Soft real-time means missing a deadline degrades performance, but isn't a total system failure.
Right.
Like digital audio streaming a glitch is annoying, but the world doesn't end.
Okay.
And firm real-time is kind of a middle ground. Missing a deadline makes the result useless, but it's not catastrophic. Multimedia applications are often like this. A dropped video frame ruins the experience for that moment, but the system recovers.
Okay, that makes sense. Let's dive into the anatomy of an RTOS. What's actually inside this kernel that makes it so powerful? What are the components?
Okay, well, at its heart is the scheduler. This is the core component that decides which task gets to control the CPU at any given moment. Most modern RTOSs, like FreeTOS or Zephyr, use preemptive scheduling. This means a higher priority task can forcibly interrupt or preempt a lower priority one that's currently running. This is absolutely crucial for meeting hard real-time deadlines.
So priority matters a lot.
Hugely. Less common these days is cooperative scheduling, where tasks have to voluntarily yield control. It's simpler, but less robust because a misbehaving task can hog the CPU. Schedulers also use sophisticated algorithms, like rate monotonic analysis for static priorities, which helps mathematically prove that deadlines will be met, or maybe earliest deadline first for dynamic priorities, allowing more flexibility. These aren't just academic concepts. They're critical for building reliable systems.
Got it. Scheduler's the traffic cop. What else?
Then there's task management. Tasks, or sometimes called threads, are basically independent flows of execution. Each one has its own context, its registers, its program counter, and its own dedicated memory stack. Tasks cycle through different states, like running, ready, meaning ready to run but waiting for the CPU, blocked, waiting for some event like data arrival or a resource, and suspended.
How does the switching happen?
That's the magic of context switching. The RTOS saves the entire context of the currently running task and restores the context of the next task the scheduler picked. This allows for rapid switching between tasks, creating the illusion of simultaneous execution, although it does introduce a small, predictable overhead.
Okay, so you have tasks running seemingly in parallel. How do they talk to each other or share things safely?
Great question. That's where intertask communication, ITC, and synchronization primitives come in. The most common one for protecting shared resources, like a serial port or a block of shared memory, is a mutex, which stands for mutual exclusion. Think of it as a lock or a token.
Only one task can hold it at a time.
Exactly. And a key feature of the mutex is ownership. Only the task that successfully locked or acquired the mutex is allowed to unlock it. This prevents another task from accidentally releasing a resource that's still being used.
Okay, mutex for resource protection. What about just signaling between tasks?
For that, you typically use semaphores. These are more general signaling mechanisms. Binary semaphores are often used for synchronization. For example, an interrupt service routine might give or signal a binary semaphore to wake up a task waiting for data to arrive. They have no concept of ownership. Any task or ISR can signal, any task can wait.
So signal received, task wakes up.
Yep. And then there are counting semaphores. These manage a pool of identical resources. Imagine you have, say, 3 network buffers available. A counting semaphore initialized to 3 ensures only 3 tasks can access a buffer simultaneously. And beyond those, for more complex communication, you have things like queues for sending data messages between task mailboxes, which are similar, and event flags for waiting on combinations of events.
Lots of tools in the toolbox.
Definitely. But using them correctly is critical, because incorrect use can lead to a classic and dangerous problem: priority inversion.
Yes, I've heard of this. This sounds bad.
It is. It happens when a high-priority task, let's call it H, gets blocked because it needs a resource, like a mutex, that's currently held by a low-priority task, L.
Okay, so H has to wait for L.
Right. But then, while L is holding the resource, a medium priority task, M, becomes ready to run. Since M has higher priority than L, the scheduler preempts L.
Oh, I see. So now H is effectively waiting for M to finish, even though H is the highest priority.
Exactly. Task H's priority has been inverted. It's being held up by a lower medium priority task. This can cause H to miss its critical deadline. This exact scenario famously caused problems on the Mars Pathfinder rover mission. Periodic system resets were traced back to priority inversion, involving data gathering, meteorological, and communication tasks. It's a real-world nightmare scenario.
Wow. So how do modern RTOCs fix this?
The robust solution is called priority inheritance. When a high-priority task, H, needs a resource held by a low-priority task, L, the RTOS temporarily boosts the priority of task L to be the same as task H. This prevents any medium priority tasks, M, from preempting L. So task L can finish using the resource quickly, release it, and then its priority drops back to normal. Task H can then acquire the resource and run without excessive delay. It's like giving a temporary emergency escort to the slow car that's blocking the ambulance.
That's clever. It's incredible how a subtle detail, like the difference between a mutex and a semaphore, or whether priority inheritance is implemented correctly, can be the difference between a system that runs flawlessly and one that crashes unpredictably. For someone just starting out with an RTOS, is it common to mix these ITC primitives up, like using a semaphore when you need a mutex? And what are the immediate red flags that might tell you, uh-oh, I might have an ITC issue brewing here?
Oh, absolutely. It's incredibly common to mix them up initially, especially mutexes and binary semaphores because they seem similar. The primary red flag is usually non-deterministic behavior. Your system works perfectly fine 99 times out of 100, but then suddenly hangs, crashes, or behaves erratically under specific, usually hard to reproduce, load conditions or timing sequences.
The worst kind of bug.
Exactly. Deadlocks, where two or more tasks are stuck waiting for each other in a circular dependency, are a classic symptom. Or race conditions leading to corrupted data values that are clearly wrong, but you can't see why. A really common sign is if you start adding debug printf statements or toggling GPIOs to trace execution, and suddenly the bug disappears or changes behavior. That often points to a timing-sensitive issue, possibly exacerbated by priority inversion or incorrect use of blocking calls in your ITC logic. The act of debugging changes the timing enough to hide the problem.
Fascinating and frustrating. So if we connect all this back to the bigger picture, how do these two approaches, bare metal with its manual control and RTOS with its managed complexity, truly stack up against each other across the critical aspects of embedded system design?
Okay, let's do a direct comparison head-to-head. First, concurrency and task management. Bare metal, as we've said, relies on you manually crafting an illusion of concurrency, often using superloops, ISRs, maybe state machines. It frequently devolves into what some call a monolithic and tangled mess that's really hard to scale or debug reliably.
The big ball of mud.
Yeah, that's another term for it. And RTOS, however, provides a formal, structured divide-and-conquer approach. You design with independent tasks, use explicit communication primitives like queues and mutexes. This inherently leads to more robust, modular, and maintainable systems, especially as complexity grows. It fundamentally changes how you architect the application.
Okay, concurrency goes to RTOS for complex systems. What about real-time performance, latency, jitter, determinism?
This one has a nuance, what I call the determinism paradox. Bare metal can offer that absolute lowest possible latency for a simple dedicated function reacting to an interrupt, for instance, because there's literally no software layer in between.
Raw speed.
Raw speed, yes. But, and this is the crucial but, this low latency is incredibly fragile. As soon as you add more complexity, other interrupts, shared resources, that predictability vanishes. The worst case response time can become very large and very difficult to calculate. An RTOS, on the other hand, introduces a small, measurable overhead for things like context switching and scheduler ticks. However, it provides guaranteed worst-case latency for your high-priority tasks, regardless of what other lower-priority tasks are doing. It ensures robust determinism.
So it's a trade-off. Potentially slightly higher typical latency in the RTOS case, but a guaranteed upper bound, versus potentially lower latency in bare metal, but with unpredictable spikes.
Exactly. Think of it this way. A safety-critical automotive brake controller doing one simple, vital thing might benefit from the raw speed of bare metal. But a complex medical device managing multiple sensors, a UI, networking, maybe alarms that needs the guaranteed and managed response times that only an RTOS can reliably provide across all those different functions with different priorities.
Makes sense. Okay, how about resource management and overhead? This is the classic argument against RTCs, right? That they're too heavy.
It used to be a much stronger argument. Let's
Right.
break it down. Memory footprint, RAM, and ROM. Bare metal definitely has the absolute minimum footprint because you only include the code you write. And RTOS introduces a baseline kernel overhead. For something common like FreeTOS, that might be around, say, 5 to 10 kilobytes of ROM, maybe a bit more depending on configuration. Plus, each task needs its own RAM for its stack.
Which adds up if you have many tasks.
It does. However, the argument that RTOSs are too heavy is becoming, frankly, largely obsolete for most modern 32-bit microcontrollers. Devices like the Raspberry Pi Pico have 264 kilobytes of RAM, ESP32s have even more. On these chips, the RTOS overhead is often a pretty small fraction of the total available memory. It's just not the blocker it once was on older 8-bit or very small 16-bit MCUs.
Okay, memory might be less of an issue now. What about CPU cycles and power consumption? Doesn't the RTOS constantly running the scheduler chew up power?
That's another traditional concern. Bare metal gives you very granular control over putting the MCU into low-power sleep states. And RTOS traditionally had overhead from its periodic scheduler tick interrupt waking the CPU regularly even if there's nothing to do from context switches. But modern RTOSs have gotten much smarter about power. Features like tickless idle mode are now common. This allows the RTOS to calculate how long it can sleep until the next scheduled event, and then put the MCU into a deep sleep state for that entire duration, only waking up for external interrupts or when a task actually needs to run. With tickless idle, an RTOS-based system can often achieve comparable or sometimes even better power consumption than a poorly optimized bare metal system that might just be spinning in an empty loop wasting cycles.
Interesting. So the power argument isn't clear-cut either. What about abstraction, portability, and long-term maintainability?
Here, the RTOS generally has a significant advantage. Bare metal code is inherently non-portable. It's tightly coupled to the specific MCU's registers and peripherals. Even using a vendor HAL just trades direct hardware dependency for dependency on that vendor-specific abstraction layer. Porting to a different MCU family or even a different vendor's chip can mean substantial rewrites.
And maintainability.
Maintainability is often a huge challenge in large bare metal systems because of that monolithic tangled structure we talked about. Changes in one area can have unexpected ripple effects on timing elsewhere. An RTOS, with its standardized API like POSIX or the FreeTOS API, offers much higher application portability. You write your tasks to the RTOS API. If you move to different hardware, you primarily need to port the RTOS's board support package, BSP, and HAL integration, but your application tasks, which contain the bulk of your logic, can often remain largely unchanged. This dramatically improves maintainability through its modular task-based architecture. Easier to understand, easier to modify, easier to test individual components.
Okay, last comparison point. The development and debugging experience. How does that differ?
Let's look at initial setup and learning curve. Bare metal can feel faster to get started with for a really simple Blinky project. Fewer concepts to grasp initially. Just write your main function and go.
Right. Less upfront investment.
An RTOS definitely has an initial learning curve. You need to understand tasks, scheduling, mutexes, semaphores, maybe queues, before you can really write your first meaningful multitask application. There's more conceptual overhead at the beginning.
But how about once you're actually debugging a complex problem?
Now the tables can turn. Debugging techniques diverge sharply. Bare metal debugging often feels like, well, low-level detective work. You're heavily reliant on direct methods. Scattering print statements through your code, toggling GPIO pins on an oscilloscope to measure timing between points, which is actually quite effective for timing.
Yeah, the poor man's logic analyzer.
Exactly. And using a standard stop mode debugger where you halt the CPU, inspect variables, and step through code, that's your primary tool. But as we discussed, halting the system can mask timing-related bugs.
Right. And debugging RTOS systems, I hear that's where things get really tricky.
It can be, precisely because halting the CPU with a standard debugger completely disrupts the real-time behavior. Timing-sensitive bugs, race conditions, deadlocks, they might just vanish when you hit pause, only to reappear when you run full speed. This is why specialized tools are not just nice-to-haves, they're often essential for complex RTOS debugging.
What kind of tools?
Firstly, RTOS-aware debuggers. These integrate with your standard debugger, but understand the RTOS internals. They can show you a list of all the tasks, their current state, running, ready, blocked, their priority, how much stack memory they're using, maybe even the status of mutexes and queues. That's incredibly helpful context. But even more powerful, especially for complex concurrency and timing issues, are visual trace tools. Tools like Percepio Tracealyzer or Say Your System View. These work by having the RTOS record events like task switches, semaphore signals, interrupt entry exits in real time into a buffer without halting the target CPU.
So you get a log of what actually happened.
Exactly. You then upload that trace buffer to your host computer, and the tool visualizes the entire system execution over time. You can see which task was running when tasks blocked, when interrupts occurred, how long things took. You can zoom in, measure timings, follow interactions. It's like having a high-speed camera recording the internal dynamics of your system. For debugging complex timing bugs or understanding performance bottlenecks in an RTOS, these trace tools are often a complete game changer.
Wow, okay. That sounds invaluable for those really tough bugs. This raises an important question, though. What about newer trends in embedded systems? We're seeing more multi-core processors even in smaller devices, and obviously strict safety requirements in areas like automotive and medical. How do those factors influence this fundamental bare metal versus RTOS choice?
That's a really relevant point, and these trends definitely push the scale heavily towards using an OS, usually an RTOS. The rise of multi-core processors like the dual-core ESP32 or the Raspberry Pi RP2040 that are becoming common introduces a whole new level of complexity that's just extremely difficult to manage effectively with bare metal.
How so?
Well, you have to coordinate tasks running truly in parallel on different cores. You need mechanisms for safe intercore communication, managing shared resources across cores, load balancing. Doing all that from scratch in bare metal is a monumental task, fraught with potential for subtle, hard-to-find bugs related to atomicity and cache coherency.
So how do ODSIs handle it?
We typically see two main approaches: asymmetric multiprocessing, AMP, where each core runs independently. Maybe one core runs bare metal code for some ultra-hard real-time function, while the other core runs a full RTOS or even Linux for less critical tasks and networking. The main challenge here is designing robust intercore communication mechanisms. The other approach is symmetric multiprocessing, SMP. Here, a single instance of the OS runs across multiple identical cores. The OS scheduler is responsible for assigning tasks to available cores, handling load balancing, and providing synchronization primitives that work correctly across cores. This generally simplifies the application programming model, as the OS hides much of the multi-core complexity.
And RTOCs support SMP now?
Yes, increasingly so. The significance of mainline SMP support arriving in popular RTOCs like FreeRTOS version 11, for example, is huge. It means a single familiar kernel can manage tasks across multiple cores pretty transparently for the application developer. This dramatically lowers the barrier to entry for multi-core embedded development compared to trying to roll your own multi-core framework on bare metal.
Okay, so multi-core strongly favors an OS. What about mixing approaches?
Absolutely. We're seeing more hybrid approaches. It's increasingly common to combine the strengths of both. You might implement extremely time-critical, hard, real-time functions directly in bare metal, often within a high-priority interrupt service routine, ISR, to get that absolute lowest latency. That ISR might then do its critical work and perhaps just pass data or a notification maybe by posting to an RTOS queue or signaling a semaphore to a lower priority RTOS task. That task then handles the less time-sensitive but potentially more complex processing, like logging the data, updating a display, or sending it over a network.
Can you give an example?
Sure. Think of an industrial motor drive. The core control loop that manages the motor's torque and speed might need microsecond-level precision. That could be implemented bare metal within a very high-priority timer ISR. But things like handling commands over a network interface, managing diagnostics, updating status logs, those are complex but less time-critical, and they run perfectly well as tasks managed by an RTOS running on the same processor. It lets you use the best tool for each part of the job.
That makes a lot of sense. Okay, finally, what about safety-critical systems and certification? Industries like automotive, avionics, medical, they have stringent standards.
Yes, and this is another area where using an RTOS, specifically a pre-certified RTOS, often becomes a practical necessity. In industries governed by standards like ISO 26262 for automotive, DO 178C for avionics, or IEC 62304 for medical devices, the process of certifying the software is incredibly rigorous, time-consuming, and expensive.
So trying to certify a complex bare metal application from scratch.
It can be done, but it's an enormous undertaking. You have to provide exhaustive documentation, analysis, and testing evidence for every single line of code, every interaction. Any change, no matter how small, might trigger a need for extensive revalidation of the entire system. Using a pre-certified RTOS commercial options like QNX, VxWorks, Integrity, or safety-certified versions like RTOS based on FreeRTOS gives you a huge head start. The RTOS vendor has already gone through the grueling certification process for the kernel itself, provided the necessary artifacts and evidence. This drastically reduces the time, cost, and risk involved in achieving system-level certification for your product.
And do these RTOSs offer features that help with certification?
Yes. Many certified RTOSs offer robust partitioning capabilities, often using the Memory Protection Unit, MPU, found on many modern MCUs. This allows you to isolate different software components, including critical and non-critical tasks, into protected memory regions. This means a bug or crash in a non-critical component, like a user interface task, is prevented from corrupting the memory or interfering with the execution of a safety-critical task, like the core control logic. This partitioning is a massive advantage during certification and recertification, as you may only need to revalidate the specific partition that changed, saving immense time and money over the product's lifecycle. Trying to prove that level of isolation in a bare metal system is significantly harder.
Okay, we've covered a tremendous amount of ground, the definitions, the pros and cons, the advanced topics. Now, the big question, if you're listening right now, maybe sketching out the architecture for your next big project, could be a new IoT device, a critical industrial controller, anything. How do you actually make this fundamental choice between bare metal and RTOS? It sounds like there's a lot to weigh up.
There definitely is. But we can break it down into a structured decision framework. You need to evaluate factors related to both the project's technical requirements and the broader development context.
Okay, let's walk through it. Where do you start?
Start by evaluating your project and system requirements. First, consider complexity and concurrency. How many distinct things does your system need to do seemingly at the same time? If it's performing a single core function, or maybe just 2 or 3 very simple sequential tasks, bare metal might be perfectly adequate, even preferable for its simplicity.
But if it gets more complex?
If you find yourself needing 3 or more largely independent, concurrent tasks, especially if they need to communicate or share resources in complex ways, think smart wearables, juggling sensors, Bluetooth, and a display, or IoT gateways managing multiple connections and data streams, then you should strongly consider an RTOS. It's built for managing exactly that kind of concurrency.
Okay, complexity points towards RTOS. What about timing needs?
Right, real-time constraints. Does your system have hard deadlines? If you have a single, critical, hard real-time requirement that demands the absolute lowest possible latency, and the logic is simple enough that you can thoroughly analyze and verify its timing manually, bare metal might be the way to get that raw speed. Think of that dedicated engine control unit example.
But what if there are multiple deadlines?
If you need preemption, the ability for a high-priority task to interrupt a lower-priority one, and you need deterministic timing guarantees for multiple tasks, possibly with different deadlines, operating in a dynamic environment, that's where an RTOS really shines. It provides the framework to manage those competing priorities and ensure the overall system behavior remains predictable under load.
Makes sense. And the hardware itself?
Crucial factor, hardware and resource constraints. This used to be the deciding factor much more often. If your target hardware is severely constrained, maybe an older 8-bit chip or something with less than, say, 32 kilobytes of flash memory, or else like 4 kilobytes of RAM, then bare metal might be your only viable option. The RTOS overhead might simply not fit.
But for more modern chips?
If you're targeting modern 32-bit MCUs, which are increasingly common and affordable, and they have adequate resources, let's say, upwards of 64 KB of flash and 8 KB of RAM, then the RTOS overhead is likely acceptable. Don't let outdated assumptions about RQS size prevent you from considering it if the complexity warrants it. The resources are often there now.
Okay, those are the technical requirements. What about the softer factors? Development team, business needs?
Absolutely. Next, you need to evaluate development and business factors. Consider your team experience and the learning curve. Does your team have prior experience with RTOS concepts? If not, and you're facing a very aggressive timeline for a relatively simple project, sticking with bare metal might be the faster path initially, avoiding the RTOS learning curve.
But if the project is longer term?
If the team does have RTOS experience, or if the project is expected to be long-lived and complex, then investing the time up front for the team to learn or brush up on RTOS skills is likely worthwhile. That investment usually pays dividends in faster development and easier maintenance later on.
How does time to market tie in, especially with external components?
Good question. Think about time to market in middleware. Is your project largely self-contained, or does it need complex software stacks? If you need things like a TCP/IP stack for networking, a USB host or device stack, a file system, maybe a graphical user interface GUI library.
Stuff you probably don't want to write from scratch.
Exactly. Most commercial and many open source RTOCs offer these kinds of middleware components as pre-integrated tested libraries, often specifically optimized for that RTOS. Leveraging this existing middleware can significantly reduce your development time and risk compared to trying to integrate or build these complex pieces yourself on a bare metal foundation. So if you need substantial middleware, an RTOS ecosystem can be a huge accelerator.
That's a big practical advantage. What about the future of the product?
That falls under long-term maintainability and scalability. Is this a simple fixed-feature product that's unlikely to change much after release? Bare metal might be fine. However, if your product is intended to be a platform, something that's expected to evolve over time with new features, new sensors, added connectivity options, then the modularity and abstraction provided by an RTOS make it much easier to scale and maintain. Adding new features as independent tasks is generally cleaner and less risky than trying to bolt them onto a complex bare metal superloop. This can significantly reduce the total cost of ownership over the product's lifetime.
And finally, the big one for some industries, certification.
Yes, certification needs. Is formal safety certification required? If not, bare metal is certainly an option. But if your product needs to meet standards like ISO 26262, DO178C, or IEC 62304, then strongly consider using a pre-certified RTOS from the start. As we discussed, it simplifies the certification process immensely. It's often the most pragmatic, cost-effective, and lowest risk path in those regulated industries.
That's a really clear framework. And I suppose as a practical tool for you, the listener, you could even map these factors onto a simple decision matrix table. Just list the factors, score your project against each one for bare metal versus RTOS, and see where the balance lies. Helps make the choice less subjective.
Absolutely. Visualizing it like that can be very helpful.
So, to try and summarize our whole deep dive today, bare metal, it offers that ultimate performance and minimal resource use, especially for those truly simple, single-purpose applications. But its apparent simplicity can be deceptive. As complexity inevitably grows, it often leads to poor scalability, nightmarish maintainability, and limited portability.
Exactly. An RTOS, conversely, is really an essential tool for managing that complexity. It enables you to build scalable, maintainable, and more robust systems through structured concurrency, well-defined communication mechanisms, and powerful hardware abstraction.
Yeah. And the futurist concurrent outlook you mentioned really seems to drive this home. That historical argument that an RTOS is too heavy is, well, it's eroding pretty fast as even low-cost microcontrollers now pack plenty of memory and processing power.
Right. And at the same time, user expectations and market demands keep increasing. Think about the Internet of Things, edge computing, richer user interfaces. All these trends are driving embedded systems towards inherent complexity and concurrency. And trying to implement that level of complexity reliably and efficiently purely in bare metal is exceptionally difficult, time-consuming, and risky.
It really feels like the central question for developers is shifting, doesn't it? It's less often, should I use an RTOS, and more frequently becoming, which RTOS should I use?
I think that's increasingly true. The widespread availability of mature, well-supported, often open-source RTOSs like FreeOS, Zephyr, Azure RTOS, ThreadX, and others, they provide such a solid foundation that they become the logical starting point for almost any new, non-trivial embedded project today.
So while bare metal will always have its niche, its place for those highly optimized, specialized, often very simple applications, maybe here's a final thought for you to consider as you approach your next project. What fundamental problems of scheduling, of resource sharing, of communication, of timing guarantees does a real-time operating system solve that you might be inadvertently recreating from scratch, perhaps less reliably, less robustly, and at greater long-term cost in your next complex bare metal project? Something to think about.